theta, and let's do it, let's do it around the x-axis so you can see it clearly. So this is the fish, and from here we have some effect of charge, and from here we have this theta, this is minus theta charge, and this is also go in the radial direction, right? Because these two cancel out and these two sum up. So I know that the electric field is actually, so electric field actually equal to some magnitude, right? Multiplied by the radial direction. For sure it's going to be radial direction thanks to the symmetry. And as we talked before, we can say that that I expect the electric field to be dependent only on the radial coordinate. Because if I'm going up at the z, I look at the world looks the same, because that z is infinite. And if I look at changing my rotation around the cylinder, changing the theta, I see the cylinder. There is symmetry of the around the z-axis, which means the world look the same for each angle that I take, and the z look the same for each height that I take. So there's no really different. The only thing that changed for me the electric field could be the distance r. So if this is a function, it's for sure function of r. Perfect. So okay, so right now we're gonna try to calculate what is the magnitude of the electric field like we did before. So what is this value? So we're gonna use again the Gauss's law. So the flux E equal to the sum of all the small fluxes from each window dA, which is to be E, the magnitude, and we said it must be a function of r, dA multiplied by cosines alpha. And now I need to choose some shape. So the trick here, how to choose shapes, it's not always working, but for most of the cases, I think 90% of the cases it's work, is if somebody give me something, I give it back to him, eye under eye. So the idea is if I see cylinders, I'm gonna use also cylinders. That's how it works for me. So here, if the fish is here, I'm gonna design area that look like this. Sorry about that. That looks like this. Okay. Envelope a cylinder around. This is not a good shape. Cylinder around my original periscope. We have the area A, and what I can say about each thing here. So let's draw here that we have also a cylinder which is bigger than the original cylinder, and what we can say, we can do it again. We can divide it to two sub-integrals. One of them is the covers, what's going up. So we have this, we need to give it some value. This is going to be r, and the height of it going to be h. Okay, so this one we have two integrals because we have up and down of this one, radius r, which is e, many e in many different locations, many different r's, dA, but I know that the electric field is pointing in this direction, the radial one, and here all the dA gonna point upwards. So I know that I have here cosines pi over 2, and this integral, and this integral is gonna die, I know it for sure, but I have other part of the integral, which is this one, which is, if I take a cylinder, I cut up and down and trim it in the middle, I can open it, and I have like a rectangular, right? So this rectangular, here it is, have the height h, and what is this length? This length is actually the circumference, because I trim it up and open it. So this is 2 pi r, big R. Okay, this is a specific R. It's not a changing R. And what is the electric field? The electric field is only the one here on this surface, right? On this here is all my small dAs, only in these parts. So this is actually E in R. It's a specific electric field in specific distance, and this is the A. So if this is a constant, I can take, and I have cosines, but I want you to look that the dA here is always in the same direction of the electric field. It's also in the radial coordinate. So the cosinus is equal to 1, so I'm just going to put here 1. I can take ER outside of the integral, ER, multiply by integral of the small dA that make this rectangular, which we already said what is the side of this one, 2 pi r. And we found the flux. This is the flux. Perfect, good job. And what is the other part of the equation, Gauss's law, is to sum up all the charge. And look here, it's a little bit tricky. So what is the total charge? Q in A over epsilon 0 equal to, we need to sum all the dq's and over epsilon 0. And what is the dq? dq is actually rho 0, which is a constant, dv epsilon 0. And if this is constant, I can take it out. So we have epsilon 0 over epsilon 0, rho 0 over epsilon 0, and we have here to sum all the dv. And now I want you to think about something. If we're going to sum all the dv, so this is actually what? The volume of my cylinder, right? Not my cylinder, but the cylinder that is being trapped inside of this, right? This is the cylinder, this one, this volume. So what's the volume of the cylinder? So the volume of it is h, right? Multiply by the base is b square pi, right? But I have here a hole, and this hole not include any charge. So and also to divide, so it's like this, subtract a square pi, right? This is actually the value of that. I can take pi outside, so we actually have this value at the end, rho 0 epsilon 0 hb h pi, and we have b square minus a square. So when we compare them, what can go out, what can go off, I can see that okay, pi falling out, right? And h falling out. Perfect. So what we got? We got that from these two, that we got that E as a function of R equal to rho 0 epsilon 0 2r, let's put this r here, okay, 2r, and this is b, what is weird for me, no, okay, 2 b square minus a square. Let's just check that this is correct. Yes, so perfect, this is the answer. Okay, so this is the electric field. Which distances this is hold? This is hold for R, which is bigger than B, right? This is what we choose. So the next question is, what is actually the electric field inside, right? Inside the cylinder. So inside the cylinder, okay, let's clean this a little bit. So I need to choose another area. Okay, choose another area. Here it is. This is the cylinder, right? So now I'm gonna choose this area, right? Let's do a top view. Top view is better. So this is my cylinder. This is the hole of the cylinder. Here I have charge, right? And now I'm gonna choose another cylinder, which is gonna be inside, in some location L, right? I remind you that this is A and this is B, right? And when I'm gonna do the flux, right, the flux side, it's gonna be the same. It's gonna be this thing. So let's leave it with the h, 2 pi. It's gonna be the same explanation that I did before. Nothing gonna change. Why? Because from the upper part and the lower part, the top and the bottom, the direction of the electric field gonna be of the dA is gonna be pointing downward or upward, and the electric field always gonna be in the radial direction, so the cosine is gonna cancel out, and we're gonna have only the circumference gonna affect us, since dA and the electric field also point in the radial direction, so cosinus will be equal to 1, and so it's ER, the electric field, multiplied by the area of this rectangular, so we got this value. But where it changed, again as the previous question, it changed in the total charge inside. You see, before we calculate all the charge inside, but right now you see that the limit of the integral change. You see, in the previous we have this equation, we had rho 0, epsilon 0, h, the height, and we also have pi b squared minus pi a squared. But right now, my top is not b, is actually r squared. Okay? So this is the only thing that being changed. I have less charge, that's the idea, because r is smaller than b. So what is if I compare them both, again you can see that pi falls off, r not falling, sorry about that. R is not falling, but h is falling. H is falling, and the full answer gonna be that E in a distance r equal to L rho 0, sorry, without the L, no L, rho 0, to epsilon 0 L squared minus a squared. That's what we got. Okay, this is epsilon r. Perfect. The last question. Okay, last question gonna be, what is the electric field here inside of this one? Okay, inside the empty space. So I'm gonna explain stuff that people do which is wrong. If I look at this, it's really easy to I'm gonna do the same idea. I'm gonna do a cylinder inside the empty space, and what I see that the Q in my new A, right, it's a new A, epsilon 0 is actually equal to 0 over epsilon 0, because the charge is always here. But what I want you to emphasize, that this alone just saying that the flux is equal to 0. That's true. That's true, there's no flux. Is there no electric field inside? I don't know. But the flux is for sure 0. Okay, so, but we know that the flux here, the same calculation gonna be, the same. It's gonna be ER multiplied by h, the height, and 2 pi r. h2 pi r is a constant. I can divide by that, and then I get that E as a function of r equal to 0. Okay, so actually the electric field inside is 0, but it's not always the case. Let's give you an example. Okay, so example is that think about let's do this. Okay, so let's have some. See here I have a bubble. Okay, some bubble, and the bubble have positive charge. So here's the bubble. So what is the electric field inside the bubble? E in equal question mark. This is a constant. So we're going to do Gauss's law. Here's Gauss's law. Right, here's Gauss's law. I'm going to do sphere because it's a given that I have a positive sphere. And I know that the charge is not radial this time. This is negative, minus r. Why? Because you see each positive charge gonna have here an effect, and you're gonna have another one here, and they're gonna sum up, and this would cancel out. So I know it's a negative, so I know that's E equal to some magnitude, but it's gonna be in the negative r, right? and yeah, and E is also equal to, E is also a magnitude dependent, the magnitude dependent on R. Why? Because the only thing that change, if I change theta, the angle that I'm looking around, the sphere is looking the same. If I change phi, it looks the same. But if I change only the distance from the middle of the sphere, from the far away or close, is the only thing that change the equation. So this is must be dependent on R. So I know how is the vector acting, right? I know that this must happen, but that's what must happen. So the flux, okay, let's leave the flux. So this is just the concept of what's happened only if the sphere is around. So this is electric field of only a bubble in the wall. But if I put here electric charge Q, let's say some electrified fish here which generate Q, I know to the every direction this charge emit electric field. What electric field? This is a dot, okay, of a dot charge. This is equal to K, right? K Q, right, over a distance, d squared. And what this gonna do? So you can see that this one here, you see that what is the flux of this thing, of the bubble? The flux is phi E equal to some geometry blah 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 blah, and we know that this must be equal to Q in A over epsilon 0, right? So this one is gonna be 0 because inside the bubble, inside my area, there's no charge at all. But I want you to look at this. The charge here do some electric field and add it to what the bubble already creates. So here you have something, here you have something. Each dA get another direction. So if here I had E dA cosinus alpha, there's no way in the world that I can tell you what is cosine alpha, because there's no any symmetry. I don't know, the electric field can go crazy here. Okay, I don't know what's going on. But I can do superposition. I can say that E is actually equal to the contribution of the charge plus the contribution of if the bubble was the only thing existing in the world. In that case, I can actually take E outside, right? Because it's depend on R, and you do this one in the lecture, right? So a Gauss of a sphere. So this is minus R and dA is outside, right? So it's a minus. So I get here that EB is, that this one is actually equal to ER minus integral dA, which is the size of the sphere. So this is a constant. I can divide by this. This is equal to 0, the total charge. So I get that the electric field, this one is actually 0, and I get that this one, if my axis is here, x, y, z, this is actually this one, k, q, r squared, right, in the direction r, from this one, right? So you can solve this in superposition, but you saw that before the superposition, this was not the case. The flux is equal to 0, but you cannot say that the electric field inside is 0. It's some exotic example, but what's really important right now is go to the homework and try to invent from your head as many areas for Gauss's equation as you can, and try to play with it. I know I think privately I think this is the most challenging part of the semester, because it's a really hard subject and it comes at the beginning of the semester. But don't worry, we're going to use it a lot, and we're going to dive it from other direction when we're going to get to magnetic fields. We're going to use Ampere law, which is really similar, and it's going to help you understand and digest this equation. So don't worry about that, just try to think about the symmetry, try to understand what is the dA, what is the electric field, and work like we did in the class. What generally the method is, look at the question and then think, okay, what is the direction of the electric field? Can I tell something about the direction? Because if you know something about the direction, you can give from your head some, whatever you want, area, that's gonna correspond to this electric field direction and cancel out some of the area which you use, or make it really simple to solve. For example, the cosine of 0 is 1, so to make sure that the cosine is going to be easy to solve, and then only calculate the charge, which we did in the first tutorial. So this is the idea. Look what is the direction of the electric field, and then think about some area to look it up. This is a really important subject to many things. So it's really important that you go through the homework and solve this one and practice it a lot. So good luck with the homework, and I'm gonna see you next week.